The next tutorial under the reaction modeler is the cross-linking reactions that we are going to see today. And to do the cross-linking reaction, the first thing is we have to model the cross-linker and the cross-linking monomer. For this particular tutorial, we are going to create an epoxy monomer which will be utilized for the cross-linking reactions, and amine as a cross-linker for this particular situations. The first thing is to create the 2D model of the epoxy. So we'll follow the same steps to create a monomer modeler for the epoxy. Just right click on it and create a new file for the epoxy monomer. And then we'll use the tabs available here and the periodic table available. You can model as per your requirement. For this particular modeling situation of the cross-linking, we are going to use the United Atom tab. United Atom tab for the modeling of the epoxy molecule here. So we are going to use the benzene of the para positions of the benzene. Here multiple positions of type of the benzenes are available: ortho, meta and para. We'll be needing the para positions of the benzene. As you can see, this will show the valency where we can connect, or you can say the valency positions available in a particular type of the benzene. So we'll be using the para positions. Now we'll create it, or we can take the model from here. And if you want to have more informations on to the tutorial, you can follow the tutorial of the cross-linking which is available under the directory of the reaction modeler in the JOcta software. And the epoxy molecule that we are going to model here is this particular epoxy resin. So we'll follow the same conditions over here in the JOcta modeler of the monomer. Similarly, we'll follow the same on the left side as well. So we have modeled our epoxy resin here. Next is to apply the force field. We are going to use the Dreading force field, and you'll be seeing that some bond parameters are empty. In such situations, we have, as you can see, this red bar is there. That means the C22, the parameters or the force field data for the C22 type of the carbons are not available. That means because the interaction between the carbon and the no hydrogen, because no such thing as a no hydrogen is available. So in such situation, we can use the options of change atom type. So here what we have to do is we have to change the C22 type of the carbon to C32 type of the carbon. and we can replace it and click on set, and it will ask whether the force field, since it is going to reset the force field depending upon the changes that you have done. So we are going to say yes, and as you can see, now no error is there. Once the force field is then applied, we can run the molecular mechanics calculations with this previous, or you can say the default conditions under. And once the calculation will be completed, the spatial coordinate of all the atoms in the epoxy resin will be calculated, and then you can visualize here into the 3D visualizer. Once the epoxy modeling has been done, then we are going to model the amine, which is a cross linker. And again, we'll be using the united atoms to model the cross linker. And for more information, you can have a look on to the tutorial file here. This is what we are modeling now. Once this is done, then again we can apply the force field. And as I mentioned in previous tutorial, that whenever we are running the any reaction calculations, we should be uniform with the force field. Whatever the force field be applied in one molecule should be same for rest of the molecule, which is going to be utilized for one particular type of the simulations. So again, we are going to use the trading force field. We'll run the molecular mechanics calculations. Once this is done, then you can visualize it. And now we are done with the initial requirement for the reaction modeler to do the cross-linking reaction. The next is to create an input file for the reaction modeler. We are going to needing, and we'll name the reaction or reaction input file as reaction cross-linking. And in the previous tutorial, as I mentioned, the same steps we have to follow. First is the registering the monomers, which is going to be utilized in the cross-linking reaction, then applying the reactive points, then setting the symmetry points, then reactive conditions. Once these things are done, then we can generate the all possible combinations of the reaction, which is been calculated depending upon the reaction conditions that we have given in the previous steps. So the first thing, or the first step, is to register the monomers that we had created in the monomer modeler. So the first one is the epoxy resin I have added here, and as you can see, next is the cross linker. So we are done with the adding the epoxy molecule, epoxy resin molecule, and the cross linker as well. The next step is to add the reactive sites where my reaction is going to take place. So the no hydrogen atom positions we have applied, this is the positions, or this is the point where my reaction is going to take place. And to add the no hydrogen atom to take place into the reactions, we have to add the conditions for the adding allowing the scission of the no hydrogen bonding. Okay, once this is done, then we'll apply the reaction sites. So this is the point, because both are the similar sites where the reaction is going to take place. At this particular positions, this no hydrogen atom will be utilized, and it will be used as an available vacancy for the cross-linking cross-linker to react with the epoxy monomer. Similarly here, so we have here two positions at this particular nitrogen atom to reacted with the epoxy monomer. Okay, so we are done with the applying the reactive sites. Next is applying the symmetry points. As I mentioned in previous tutorial, these symmetry points helps us to reduce the computation cost. Okay, so we are going to apply and tell the system these points are symmetrical points. Okay, so this is the first point, this will be the second, third. You can define as per as you want. Okay, similarly, as you can see, this is the first symmetry points, so we are going to follow here same, the first, second, and fourth and fifth. That means our simulation will run for this particular one particular side, and it will be replicated for the other side to reduce the computation cost. So we are done with applying the symmetry points for the epoxy monomer. Next is applying the symmetry sites for the cross linker. Since no such extra is there, so these CH2 molecules are similar, so we have applied the symmetry points. So we are done with the 3 steps: registering the monomers, applying the reaction points, applying the symmetry points, and then setting the reaction conditions. So from here, this plus button, we can add the reaction conditions. So what we are going to do is make the system to react this one point with this point of the reaction of the cross linker. So we have chosen the epoxy as a monomer 1 and the reactive site is 1, and in the cross linker the reactive site is 2. Okay, and from here we can apply the conditions. Okay, from here we can choose the threshold distance. For this particular simulations, we are going to make it as 4 angstrom. I want my reaction to take place completely, so probability, we are going to use this particular simulation the probability conditions for the reaction, and we'll be keeping the other thing as a same. We'll just save it. So we are done with applying the reaction conditions for the cross-linking reaction. Once this is done, then we can tell the systems now you are good to go to do the reaction. If you click on to reactive generation, as you can see, multiple possible reactions are going to take place, which will be a cross-linking positions. As you can see, it has generated this. Once the possible post reactions are been generated, we can apply the force fields again, and as you can see, the similar situation is again available here. Okay, so again we'll be using the same. We have to replace the C22 type with C32 type. I'll replace it, click on save, and it will be gone. Click on the save button. Once this is done, then we are good to go with creating the input file for our cross-linking reactions. We are going to keep each and everything as a by default only, and the important tab is the polymer tab, will be where we'll be creating the input file by adding the number of epoxy monomers and the cross-linker. Here we are going to add the 20 monomers of the epoxy monomer and the cross-linker as only 10. Once we apply the polymers 20 and the cross-linker as a 10, and under the simulation conditions are going to be the same, and the boundary conditions, we can make our system to be more susceptible to the optimizations. So we are going to create a density of around 0.5, and then we are going to create our input file. Once the input file has been created, we can open it, and as you can see, it has added the number of epoxy and the amine group monomer. Our system is ready. The next thing is to relax the input file that we have created for the cross-linking reactions. Once our system is relaxed in terms of energy, in terms of density, and once it is done, then we can do the cross-linking reactions with the help of the VSOP engine. So we have already applied the simulation conditions while creating the input file, and next is to choose the type of the VSOP engine. So right now we are using the VSOP engine, and as I mentioned, we have to first relax our simulation box. So that's why we are going to turn off this flag of the reactions, and we can run our simulations. We'll wait once the reaction completes, and later on we can go on to do the cross-linking reaction for this particular system once the system is been properly optimized. So once the relaxation has been completed, we can open it, and as you can see, the total energy is been relaxed. So once the relaxation has been completed, we are going to take the last frame as a input to the next step. So for that condition, we have to go to the last frame of the output file for the relaxation, and then we can click on edit with Cognac modeler, and it will ask which frame you want. So we need the 100th frame, and we can name the output file, since this is an output, and will name as to react next, and then click OK. So this is the input file. We can again run the same relaxation for the density calculation optimization as well, since this density we have given to the system. But just to showcase the same situations, we have to give the conditions here, simulation conditions, and choose the proper algorithm here, dynamic algorithm, to do the optimization or the relaxations. First, for the energy relaxations, you can use the NVT algorithm, and to optimize the density, you can use the NPT algorithm. And then once it is done, you are good to go to do the cross-linking reactions. And again, since we have the available data, and next is to allow the system to come closer and react with each other, we have to change the dynamic algorithm from NVT to NPT, as I mentioned. Once this is done, and then we can click on to the running of the simulations. We have to choose the VSOP engine. As I mentioned, VSOP engine is used for the cross-linking reaction. So we have to start it, and here, as you can see, now we are ready for the cross-linking reaction to take place. So we have to turn this flag on and keep the rest of the parameter as it is. Once this is done, we can click on the start VSOP. So as you can see here, the cross-linking reaction has taken place, and its conversion is taking place from the VSOP file to the Cognac file. Okay. So once the reaction has been completed, you can take the output file, and as you can see, density was going to getting increased since we ran only for the 10 picosecond. It has not been properly optimized, but we wanted to show you how this cross-linking is taking place. Okay, to see, as you can see, we added only the epoxy and the amines, but we have the 3 types of the molecules are available. So let's just see the molecule 34, and as you can see, it has bonded. If we remove the boundary condition, as you can see, this amine has reacted with one epoxy monomer of this, whereas let's check the other. As you can see, the cross-linking reaction has taken place, and even as in the previous tutorial I shown you one script of the how many bonds are formed, that can be seen via this particular script. And if you want to find out the script, so that script is available into the tutorial. As you can see, this tutorial is available over here. You have to just copy it and make the proper indentation. Once you have applied the indentation and click on to run the script, you will be seeing the number of moles, number of atoms, and the number of bond. Initially we had the 30 number of molecules, 20 for of the epoxy monomer and 10 the amine, and number of atom was 580, and number of bond initially we had 590. And as you can see, the reactions are taking place, so the number of bond is getting increased to 60616, and at the end the number of molecules remained is only 6. If we run for sufficiently long time, all the molecules will react with each other to make one particular only one molecule, where the cross-linking will be completed. So this was all about the cross-linking reactions, how to set the conditions, how to model the initial requirement for the cross-linking. You have to just model the monomers, apply the conditions for the reaction modeler, give the symmetry points, apply the conditions, and then you can create the input file for the reaction modeler, and then optimize your simulation box. Thereafter you can run the reaction modeler with the help of the VSOP engine, and you'll have your cross-linked molecule, or the cross-linking has been completed. Thank you.